Good morning, everyone. Welcome to this first talk titled Offset and Azimuth Diversity, a Recipe for Complex Imaging. As Dave said, my name is Chris Page from PGS and co-author with Ivan Fromyer. And we're presenting the following. So, the other pointer's got a little blank out key in it. This one hasn't. Oh, yes, it has. Yes. Sorry, I just wanted to say something before I went on, and if I had the slide up, then I notice your attention goes to there. So what we're trying to do with this presentation is just to give you a brief snapshot of some of the things that we've been involved with, most recently with subsalt and wide azimuth. So that's what we're trying to do today. And so I'll give you some background as to why we've chosen that talk. Then we'll be talking about wide azimuth acquisition styles, of which I'm sure you know there are many. But we'll be talking about two in particular to give you an idea of the range of towed streamer styles that are available. Then I'll be talking about crystal WATS, which is 3 Gulf of Mexico wide azimuth surveys, phase 1, 2, and 3. And then some aspects of wide azimuth pre-processing, because as we acquire wide azimuth, we need to adjust our software not only to be able to process wide azimuth data, but also to take advantages of it. So a little bit about that. Then some data examples, recent developments, summary and conclusions. The talk is supposed to last about half an hour, and there'll be time for 5 minutes talk afterwards, I believe. Questions and answers, that is. Okay, here's some background to why we've chosen this collection of things to show you today. So the first one is that subsalt exploration has gained momentum due to a number of large discoveries, which I'm sure most of you are aware of. And also subsalt imaging has improved significantly with modern depth imaging technology and processing. So this has allowed us to realize some images which we weren't able to realize before. The challenges that remain then, the challenges mainly are poor illumination from conventional acquisition, and the complex multiple wave field which interferes with primary. So this slide here is from Bernstein, 2008. Really, this is just to give you a quick overview of some of the large discoveries that have been made recently, and this particular slide is drawing an analogy between the west coast of Africa and offshore Brazil. And it's pre-salt. You'll notice there that there's the thing on the top left there summarizes some of the recent finds. Tupi in Hiroshima, for instance, 9 billion barrels. So these are large finds that have been made recently. So now, why would we want to shoot wide azimuth in pre-salt? So this is a little explanation of that. The first reason that's often quoted is illumination. And the top left there is a view through a typical complex salt area. That's a subline and a cross line you're viewing there. And you'll see that the salt is quite complex. That's the salt in brown, for those of you who aren't familiar with that. And the top middle there is an azimuth plot for dual azimuth acquisition. If I can look at the scales here, we go from 0 offset to maximum offset this way, radially. And then this is azimuth, source receiver azimuth. So you can see we've got east-west and north-south acquisition there. You may notice that the azimuth range is wider on the near offsets. That's because the azimuth to the near traces on the far cable are larger and get smaller as you go down the cable. Contrast that with the wide azimuth illumination top right. You'll see that's a much better sampling of azimuth. Although it's 4 times the acquisition effort. So why would we want to do that? Well, the bottom right gives you an illumination map of a target horizon. So we're looking at how many of our nicely sampled seismic rays hit our target, and it's quite smooth on the bottom right. Contrast that with the bottom center, which is dual azimuth, and you'll see there's some holes. There's some holes here, holes up here. And the way that manifests itself on your final migrated image is you'll see some data, and then there'll be no data at all. And then you'll see the data continue. So you'll have no data zones, if you don't acquire enough azimuths in complex salt areas. So why should that be? That's the purpose of this little diagram in the bottom left there, where this little star represents a shot, and we're looking plan view, where we're looking at the wavefronts going down to a target horizon and seeing what comes back to the surface. And what comes back to the surface are those little red marks. So in this 6 kilometre radius, this is where the rays hit the surface, and all around here, nothing hits the surface. So if you were to have an acquisition geometry with receivers around here, you would get no seismic at that particular point in the subsurface. So this typically is what happens, especially in complex salt areas. You may get areas where maybe there's a preferred acquisition direction to give you better illumination, but in general, because as the salt changes, implanted on that perhaps preferred acquisition direction is this more complex illumination, which changes as you go through the survey. So in order to get good illumination over complex areas, you need to acquire as many azimuths as possible to maximize your chance of illuminating that. And then on to multiple diffractions. So this is the second reason given for acquiring wide azimuth in complex areas, and that's the attenuation of multiple diffractions. Actually, it attenuates multiples in general, but multiple diffractions tend to be the big problem. What I'm showing here is, I'm sure some of you have seen already, it's from Carl Rigoni, 2007, and here finite difference modeling was used to generate seismic data, which was then preset depth migrated, and we're looking at depth slices. So on the left, this was acquired with narrow azimuth, and on the right, it was acquired wide azimuth. And you can see that it looks a lot cleaner on the right, the signal looks a lot stronger, and it looks a lot less noisy. Subsequent to this being published, and acquisition in the same area, real seismic acquisition, has shown that we have a very similar relationship between this synthetic data and the real data. What you'll notice then is, if I can just point to the screen, this is being recorded, so I'm trying to speak to the speakers as well as look at the screen, so excuse me if my face looks a bit strange. So this is noisy, but you also see some of these circles here which aren't present there. And the reason for this is that, so if this is the surface, and this is a multiple, we migrate the data with primary velocity, which is too fast in general for the multiple, so the multiple over migrates. And then when we take a slice of that, we see a circle. So that's the thing that wide azimuth is good at attenuating, the steep limbs of those multiple diffractions. So why streamer surveys? Some of you will argue strongly, I'm sure, that why not ocean bottom cable? That gives you good wide azimuth. Except, of course, streamer surveys can be very efficient. And so there have been a lot of different acquisition scenarios proposed because with streamer surveys because they're so efficient. And the one this here is an aerial view of a tile geometry, which I'm going to be talking about as one of the two geometries in a moment. So we're going on to wide azimuth acquisition styles. Oh, two in one go. So pretend you didn't see that little slide just there. And so this is the basic behind the tile geometry. We have a streamer vessel with no source on it, and then we have two source vessels. So it's three vessels altogether. You could say that equates to about twice the cost of a normal streamer vessel with sources on it. Each source vessel has two sources in this, flip and flop. So with 120 meter streamer separation, as in this example, one shot would give you 60 meter subsurface, flip flop gives you 30 meter subsurface, and you can stagger these two source vessels and get 15 meter subsurface quite easily. So with this geometry, if you need fine crossline spacing, it very readily gives you that, whereas other geometries which require a better azimuth distribution aren't so good for smaller crossline bins. Although, as I'm sure some of you are aware have been involved in it, when you're looking sub-salt, you're usually looking at low frequencies, and so maybe you don't need such fine bins, but nevertheless, depending on your area of interest, it's one advantage of this system. So that would be called the first tile, and then we reacquire that with the source vessels in the same positions. And we move that streamer vessel down 1,200 meters, and that's the second tile. And that generally was repeated for between 2 and 4 tiles. So we had 3 vessels compared with conventional seismic as opposed to 1, so that sort of doubles the price. 2 tiles, you spend twice the amount of time. So you could say, roughly speaking, this is 4 times the effort. Because then we move up the same as we would do with conventional seismic, 600 meters, and we repeat it. So this is a 2-tiled acquisition, and for this type of acquisition, which was acquired on one of the surveys we're going to show you later, you don't need to read all of this. The key things are that this is the azimuth recorded, the azimuth range. You have the streamers here and a source here, and it records that azimuth range. Then you have the streamers here and a source here, and it records that azimuth range. So it's just azimuths recorded in the bottom here. And the fold is 108 if you look at a 6.25 by 30 meter bin. Those of you familiar with processing seismic will say, well, we don't normally process that size, but bear with me, I'm just making that comparison to make it easy to compare to the next one. So it's 108 fold. Typically you'd process that maybe 12.5 meters by 15 meters. It'll be the same fold. So now here's a next geometry. This is called dual streamer anti-parallel. It's a little bit more complicated. We'll be talking a little bit more about this one. So we start with 2 streamer vessels. So it's going to cost you a little bit more. And we have 2 source vessels, as we did before, but we have a single source on each vessel. Still 4 sources. Because we don't have flip-flop, we don't have that reduction in cross-line spacing. So in fact, the cross-line spacing in this case would be 60 meters. So we shoot that, and then you'll notice that the sources are all on one side of the cables, unlike the tiled. In the tiled acquisition, we have a source on one side and a source on the other side of the cables, the far end. Here it's the near end only. And so to give us the azimuth distribution, we sail alternate lines in alternate directions. That gives us this azimuth distribution recorded, which is better than the previous one. So you could say, in terms of costs, I'll try and go back to the conventional seismic, which would be a single streamer vessel with source on it. You could say that since we've got 2 streamer vessels, it's got to be twice as much, plus 2 source vessels, maybe 3 times as much, as opposed to the tiled, which is only twice as much. But the tiled one, remember, we repeat the tile, which makes it 4 times the cost. So this is quite cost-effective, larger bins, and pretty much the same trace density. So the nominal fold, 184, is quoted for 6.25 by 60 meter bins. The cable length is a bit smaller. If you do the math, basically it's the same trace density as the 2 tiled we just shown, only it would be acquired in half the time, sorry. So this is more efficient to acquire, but you need another vessel during that acquisition. The other nice thing about it, if you're processing the data, is that it's got more near trace offsets, which is always nice when you're trying to tie down velocities. I'm talking a little bit more about this acquisition then, because the previous slide maybe misled you a little bit because this acquisition is staggered. As you can see, there's the 2 streamer vessels. The staggering in this diagram is exaggerated so that you can see it. In fact, is only 37.5 meters between each vessel. But this gives you an idea of what we do, and this is crucial to how we process these vast amounts of data. So there's a little animation here. The first shot goes off, we move along 37.5 meters. The second one goes off, and you'll notice that these are in line. We continue in the next, so each shot goes off. There's a shot going off every 37.5 meters. And there's just 2 rows of shots we're showing in that animation. We then come back in the pink direction, and we fire shots in between, and all these shots nicely lining up. So by moving up by 600 meters, we fill these shots up. When we come back the other way, we cover the same source position. And by covering that same source position, we eventually build up. This number here is 4, so we cover each source position 4 times. Now, the significant part of this is that when you're migrating, when you're doing pre-salt, you need to have one of the most expensive algorithms that we can have, and it takes a long time. And of course, who wants to spend a lot of time waiting for the processing to be finished? It turns out there's a little trick with these expensive migration algorithms, is that you can put more traces into a shot and it doesn't cost you any more. You do the transform and you can have twice as many traces, 4 times. In this case, 8 times as many traces in the shot record, and it costs you the same amount of money. So you get an 8 times speed up. And just to illustrate that, this is the super shot, the blue being traveling to the right, and those are the subsurface positions covered by that. We collect all those traces together and migrate them in one go. And then there's the orange one going to the left. So that enables us to process the data more efficiently with the expensive migration algorithms. So we're just going to be talking about those 3 surveys in the Gulf of Mexico, Crystal Phase 1, 2, and 3. So here we have, this is the Gulf of Mexico, plot here. Here we have Crystal Phase 1, 10,000 square kilometers, Phase 2, and Phase 3. Phase 1 and 2 were acquired with 2 tiles in the tiled acquisition, and Phase 3 was acquired with a dual streamer acquisition. And we'll show you some examples of that. So really, depending on your target, you need to decide what kind of acquisition style you're going to use to be the most efficient. And this just gives you a couple of examples of what's possible. So moving on to some aspects of wide azimuth pre-processing. There we go. So here we have a standard processing route, source designature, debubble, seismic interference, attenuation, true azimuth 3D SRME. I'm going to be talking a little bit more about that. Then enhance, high resolution, I should say, radon demultiple, multiple diffraction attenuation, water column statics, etc. And then I'll be talking a little bit more about the tomography. I just wanted to pause here because when wide azimuth was first touted a few years ago, many people were saying that, oh, it's so great at attenuating multiple diffraction energy that you don't need to apply SRME. In fact, you don't need any demultiple. And I've just told you it's great at attenuating, and I've shown you examples it's great at attenuating multiple. So why are we applying true azimuth 3D SRME? Well, pretty much a year after some people had said, oh no, you don't need any demultiple, it was unanimous really amongst contractors and oil companies alike that you do need to hit the multiple as much as you can. So you need to hit it with wide azimuth acquisition, you need to hit it with 3D SRME, you need to hit it with enhanced high resolution radon demultiple, you need to hit it with multiple diffraction attenuation, so you need to keep hitting this to reduce it. I'll show you some examples of those stages, some of those stages as we go through. So, and I'll be talking about the tomography and the updates you need to handle wide azimuth. So we move on to true azimuth 3D surface-related multiple prediction. So I'm sure some of you have seen these pictures before, and I'm not quite sure what they mean to some people. To me, it's the simple thing is if you have for every source and receiver pair you have a recorded seismic trace. With SRME, we predict another trace, a second trace which has the multiples in it for that trace, and we subtract them out. And we do that trace by trace. Now, how do we predict those multiples? Well, for this source, we take all the traces in that source gather, every single trace in the source gather, and then we convolve it with every single trace in the receiver gather. So we have to recognize which traces those are, and we convolve each trace with each other, and we sum the result. And that gives us the predicted multiple. Now, how big an aperture should we be using? How many traces do we need to sum together? Obviously, if we require wide azimuth, there's the opportunity to do it over more traces. And what's the advantage of that? Well, the advantage comes from attenuating multiple diffractions. So you need basically a large aperture to predict those diffractions. So the larger the aperture, the more diffraction, the steeper dip of the diffraction you're going to predict. So that governs the efficiency of the algorithm. And so that's the way it works. With narrow azimuth, you have a much smaller aperture recorded in terms of traces in a common shot and traces in a common receiver. So wide azimuth certainly helps in that. But your SRME needs to take that into account. So the challenges with 3D SRME are the coarse sampling of cross-line sources and receivers. Because as we add these traces together, ideally we'd have a complete fine sampling of sources, maybe every 25 meters, and a complete fine sampling of receivers, and otherwise you get aliasing. So to address that coarse sampling, you need to have good 3D reconstruction schemes. And the limited crossline aperture, the only way of really benefiting from that is to acquire wider azimuth data. Here's some examples then. I talked about wide azimuth attenuating multiple diffractions. This is a wide azimuth survey that's been preset depth migrated, and it has radon demultiple applied. So it has a demultiple applied to it, and it's been preset depth migrated. And then the next section I show you will be the same, only with the addition of 3D SRME, true azimuth 3D SRME. So you can see the difference there. I went back too far, look at that. Sorry. So, excuse me. Yes, thank you. So, so this is without SRME, and that's with. So you can see these, which are over-migrated diffractions I was talking about earlier, are nicely attenuated by the 3D SRME. Here's another example. The same thing again. The diffractions aren't showing so clearly here. It's more and more now manifesting itself as what looks like random noise, but that's the benefit. Sorry about the slow animation here. So that's with and without 3D SRME. So that's the benefits. That there's still something left there, and that's the need for the final multiple diffraction attenuation. Okay, now I'm going on to depth velocity model building. So in order to get the good results, we need to have the best model, and we'll show you an example of how much that can impact the final image. And you need the best algorithms. So this is a standard sequence here for getting a velocity model. I'll just go through it. It's very simple. We start with an initial model. Then we calculate travel times. We migrate the data with the initial model. We then look at residual errors. We put those errors in the tomography to come up with an updated model. And then we remigrate, which is what this is. So depending on the complexity, we need to use the appropriate algorithms. And typically in complex source areas, there's deep water. You don't need expensive preset depth migration to go through the water or through the sediments. And if you were, it would take a long time, and who wants to spend a lot of time on data processing? So the initial velocity depth model, for the overburden, we tend to use a high-density grid-based tomography, which is much quicker than what we need for the final migrations. We then, for top salt interpretation, we use cheaper methods like Kirchhoff and Beam. And then for salt flooding, I'll talk a little bit about that in a moment. We use turning ray, Kirchhoff and Beam. Basically, we have to image the sidewalls of the salt in order to position that correctly before we can do the analysis of the salt on the other side of the sediment. And that's what this smart flood is called. I'll talk a little bit about that in a moment. And then right through to the final velocity analysis, wave-field extrapolation migration for subsalt velocity analysis. So what are the sort of updates we have to do to our tomography for wide azimuth? It becomes more important to recognize our source and receiver positions. So what does tomography do? I'm sure most of you are familiar, but I'll just do a little refresher. So what we do is we migrate with a guess velocity. We then look at errors. And then tomography takes a source receiver and it distributes those errors along that travel path. And it does that for each source receiver pair, and then it comes up with a solution for the next model. With wide azimuth, with narrow azimuth, source and receiver would be pretty much in line. With wide azimuth, it could be a receiver over here or a receiver over here. And if you're talking about directional sensitive velocity, you need to take this into account. And so what you need to do is to, instead of binning on common offsets, you bin on common vector offsets. And all that means, for those of you who aren't mathematicians, it means you look at the inline offset and the crossline offset separately to come up with a vector. And so by binning the data like this, we can then look at the effect of each one of those directions and update the model accordingly. So for true azimuth tomography, you need to input, to generate these vector offsets, you can input those and generate them from either fast beam or Kirchhoff migrations. The vector offsets is an extension to standard narrow azimuth processing, where the cross-line offset will be virtually zero, so it will handle narrow azimuth, multi-azimuth, and wide azimuth. Then you use an updating procedure, either residual move out of the gathers you just migrated, or picking delta Z errors directly, and you put that into your tomography. And you use the acquisition geometry to work out where you're going to put that, which volume you're going to put those errors into. Now, this iterative procedure isn't necessarily unique. It won't necessarily come up with a unique solution, and so you need to stabilize that in some way to hone that down to the solution you're looking for. And we do that by, it says here, inversion by preconditioned conjugate gradient solver. So I just want to divide those two out. Conjugate gradient solver is a way we solve it, but the key thing here is the preconditioning. And what you need to do when you're solving, especially in complex salt areas, you need to allow the velocities to change rapidly in the vicinity of salt wall. So if this is sediment and that's salt, you need to allow the velocities to change rapidly, which typically makes the whole thing less stable and less unique. However, if you can have a space variant stabilizer based on the amount of velocity you expect change you expect over a certain area. In the sediment areas either side, so if this is salt and salt, sediment in between, you can afford to have a wider range of velocity gradient, can be less steep here, and then you need to allow it to be very small here at the salt wall. So by allowing a space variant based on your interpretation, variance in the rate of change of velocity, it allows you to pick accurate velocity around the salt wall and also stabilize it in the sediment and within the salt areas. And so that's a little trick you need to do in order to come up with fast varying velocities but a stable result. Here's an example of that. There's some migrated gathers at the top there. On the left is the 3D plot with transparencies of the residual errors on the first iteration, and on the right it's the third iteration. And this is the sort of QC you have. The seismic section would be the migration with your latest velocity model, and you pan through that to see where these errors are occurring and help you update your model. I said I'd talk a little bit about smart flood, and this is an example. And so what does flooding mean? Those of you who aren't familiar, those of you who are familiar know what I'm talking about. Those of you who aren't familiar, what we do is we interpret the data and then we give it a velocity. And typically you'd have to interpolate these salt bodies. This is the salt in here, and this is the salt in here. So you'd have to interpret that, and then you'd put salt velocity in that in your model, and that's called flooding. However, you need to know where that salt boundary is, and that's not so easy. So smart flooding, if you're using beam migration, you can select rays that are only on this side. You can reject rays that go through the salt, and just choose rays that go through the sediment, and migrate the whole thing with sediment velocity, even the salt. But because you selected rays that went through the sediment, the salt wall is then positioned correctly. And it's usually easy, relatively easy, to pick the sediment velocities. So you've got some kind of confidence in that salt wall position, and you use that before you flood the salt with salt velocity to see the pre-salt data. So that's a little thing you can do if you're using fast techniques like beam migration as part of your velocity model building. So some data examples. How am I doing for time?
Oh, you've got another 5 minutes. Is that enough?
Yeah, definitely. So is there 5 minutes talk after that?
5 minutes talk, and then 5 minutes for questions.
Oh, I'll smack on time then. Great, thank you very much. So this is some legacy narrow azimuth data. So in this particular area, we had some narrow azimuth, and it's migrated with our best velocity. And what we did then is we reacquired with wide azimuth, and we used this velocity field as our first migration velocity field. So the next section I'm going to show you is the same velocity field, the same processing, but wide azimuth data going into it instead of narrow azimuth. So that's the difference. So this is what wide azimuth buys you: narrow azimuth and wide azimuth, and this is wave field extrapolation, pre-stack depth migration. So you can see there's a significant update. Now, if you then, that's the narrow azimuth and that's the wide azimuth. I'm a bit finger happy here, sorry about that. I'm showing you the next slide, which is in fact the same wide azimuth data, but using the wide azimuth to pick the velocities. Obviously, with wide azimuth data, you're going to see much clearer data, so your velocity model is going to be much better. Point I made earlier on in the presentation, the velocities are critical. So this is the narrow azimuth velocity and the wide azimuth. Sorry, I'm not being patient enough. Narrow azimuth and wide azimuth. You can see the significant difference there. So this is what happens when you use wide azimuth for velocity analysis. This isn't the final one, this is an intermediate, but you can already see there's the salt in here that we're trying to image. So that positioning of the salt and the thickness obviously affects the fidelity of the structure down here. So further improvement is using anisotropic migration. This is wave field extrapolation migration, and the next one is reverse time migration. I just toggle between those two, and you can see again here we have the salt wall, and you can see with the RTM. So that's wave field RTM. We're seeing much better imaging of the salt walls. So our final migration tends to be, with these wide azimuth subsalt plays, reverse time migration with anisotropy. Okay, recent developments. So when I say recent developments, this is the sort of things we were doing last year to give you an idea of how at least PGS has progressed, and I understand other contractors are pretty much similar. So the processing here is pretty much what I talked about before. The key elements of this are TTI, sediment overburden modeling. I'm going to talk a little bit about TTI. True azimuth tomography, multiple salt body definition, so you can define the salt bodies separately, subsalt velocity analysis, TTI, RTM, TTI beam. I'm one of those people, I'm not very happy with these little three-letter acronyms. So I'd like to talk a little bit about TTI because it's really quite a simple concept. So to order explain that, I want to talk about constant velocity. That's the simplest model you can have. So if you have a body here with constant velocity, your rays will be straight. The next complexity is if you have horizontal layers, increasing velocity, and your rays will bend. They won't bend sideways if the velocity is constant in those layers, but you'll have ray bending. If the velocity varies in those layers, then you would need depth migration. The next level of complexity is if the horizontal velocity is different from the vertical velocity. And typically we look at what's called VTI, which is vertically transverse isotropy. Bit of a mouthful, but it just means the horizontal velocity and the vertical velocity. There's two velocity trends, a fast and a slow velocity trend. Typically the horizontal is the fast one, and they're perpendicular. So TTI is tilted transverse isotropy. Is that only tilted? So that's what it is. It's a slight update, but it allows us to handle much more complex velocity models in a reasonably stable way. So that's pretty much state of the art, TTI reverse time migration and TTI beam migration. Here's an example of what that TTI gives you. So this is reverse time migration, an expensive preset depth migration process. And the next one, we're using anisotropic, that's a TTI velocities. So I've jumped too many, sorry about this. So that's the reverse time migration, and this is TTI. And what you'll see is that the salt is much better defined here, but also we're seeing general positional differences of the order of 400 meters, which I think you'll agree is significant if you're trying to put your 9 5/8 casing down. So, in conclusion, so we can show that conventional data and wide azimuth has delivered improved illumination when you compare the two, better multiple suppression and better signal-to-noise ratio. And the wide azimuth processing flow includes wide azimuth tomography, TTI compliant, wide azimuth SRME, beam for fast model building, wave field extrapolation migration, and reverse time migration. So thank you. I'd like to say thank you to PGS first for permission to present this paper. Thank you for Finding Petroleum for inviting us, and to many colleagues at PGS who've helped with this presentation, and thank you for your attention.
Okay, any questions? Professor Jack, I think.
Thank you very much.
Be gentle with me, Ian. You know.
Okay, so Ian Jack, mostly retired. If we add your paper to the dozen or so other excellent presentations on wide azimuth results that we've seen over the last 4 years or so, it's a really compelling story. So I would propose that one of your conclusions could have been, additional conclusion, could have been that really, since these boats are quite expensive to tow with long cables and so on, that we should really just be concentrating our efforts on cheaper systems of putting cables, permanent cables into the ground, like distributed optics or such like. So the results are then, the results are intuitively obvious that we should be doing that. And would you like to comment?
Yes, no, thank you. That's a good point. I think related to your question, though, is, so what would we like to do ideally? I showed you 2 expensive wide azimuth acquisition schemes, which are towed streamer, and which are a lot cheaper than, say, ocean bottom cable and finer sampling. But yet, they are not what we would like to do ideally. What we'd like to do is a lot more than that. So we really are, with our wide azimuth, we're cutting the corners to the bone to get you the data you need. And so ideally, theoretically, we'd want to acquire a lot more data, and I guess oil companies aren't prepared to pay that money and time, because they can get an almost acceptable product by acquiring less. Now, so it's a money thing, I think. Certainly, ocean bottom cable can give you much better azimuth distribution and can be, depending on what kind of tow streamer solution you're suggesting, can be more expensive or can be comparable. So it really depends on the resolution you want. So I prefer to think of it in terms of what's your problems, what's your resolution. At that time, knowing the area, you can propose different solutions. So, but for 4D, of course, if it's an existing installation, you wouldn't want to put ocean bottom cables down in an exploration area, maybe, until it becomes a lot cheaper. But certainly for 4D, yes, I agree with you. Fixed cables might be a better solution.
David?
Thank you. David Jenkins. With that very complicated surface geometry, what's the sea state limitations for you?
That's a very good question. That's a good, I mean, you're asking someone at PGS who say, well, tow with GeoStreamer, because you can tow deeper and you can tow reasonable quality data in less sea state. I'm sure other contractors would tell you the same. It is, of course, key, because there's no point in towing something complicated if it's going to get all tangled up in bad weather. However, it's just 2 streamer vessels separated by a large amount, so it shouldn't be any more difficult in terms of sea state than towing a single streamer vessel. What becomes a little bit more complicated is the navigation control and things like that. But my understanding is that those controls have been beefed up to do a lot of that automatically. So it is a bit more wide for the people involved in acquiring the data, making sure it adheres to those standards. But basically, 2 streamer vessels is not a big issue over 1 streamer vessel if they're far enough apart and so the streamers can't get tangled.
Over there.
Ed Tree, mostly working. When we look at 3D surveys in non-complex geology, we also see substantial improvements with wide azimuth in many cases. This could not obviously an illumination problem, and I believe that there's 2 reasons for this. One is that with multiples and wide azimuth, we see a much greater density of long offsets in the output bin, so it weights the data. And in fact, I've seen examples where narrow azimuth 3Ds have been improved simply by weighting the longer offsets. But the other reason, I believe, is due to the fact that the stacking process enhances scattered noise from various azimuths, but specific azimuths. And that by having multiple azimuths, we add together some scattered noise that is being enhanced with a lot other which is not being enhanced, and that's the reason we see the benefit. And we're seeing that very often in land because of near-surface variations. And we see it sometimes in the North Sea where you have a lot of terminal moraine deposits in the near surface, just below the sea surface. So I think we could add those as extra reasons why we'd want to do the wide azimuth work.
Yes, it's interesting. If I can just summarise some of that. So the first issue is a lot of wide azimuth geometries, and I didn't show that so very clearly, actually require more far offsets than nears. This gives you an offset weighting, which in itself attenuates diffractions, multiple diffractions in particular. And so in order to compare multi-azimuth, which is a selection of conventional data, against wide azimuth, it's been demonstrated, I think by BP, either last year or the year before, I think beginning of last year, that if you take this offset weighting into account, multi-azimuth and wide azimuth are very similar. Nevertheless, multi-azimuth then against a single azimuth, you do have more azimuths. And even on conventional data, as you say, you do actually see some speckled illumination differences, plus you see some benefit for having more azimuths. So the other issue is the offset issue in terms of the noise attenuation, because as you will see, if you have a recorded trace source and receiver here, the migration smile is large in this direction and small in that direction. And so by sampling several ones, this large part of it tends to get attenuated and you're left with the cusp. And the cusp is easier to attenuate with conventional processing. In fact, conventional processing attenuates the cusps quite nicely, and it's the wide azimuth which attenuates those little bits of escape.
Just one, I suppose in a way, more geological question. I mean, if you look at the combination of conventional seismic, multi-azimuth, wide azimuth, and so on, are there any geological problems left untackled offshore, do you think? I mean, we can do steep dips, we can do close to salt, sub-salt, sub-basalt, maybe? I don't know. Is it kind of, in a way, is the question, another version of the question Ian was asking, I think. You see so many papers with fantastic acquisition and then the processing taking care of it, that it looks like any geological problem can be solved offshore. Do you think that's right, or am I exaggerating?
I think that the key thing is, you mentioned basalt, and the key thing is penetration. I've seen a lot of areas where there's been salt clouds. You don't see beneath a salt cloud, a gas cloud in an oil field, and you don't see much data. And some people say, that's because of penetration. And really, the data's been so absorbed that you haven't got enough dynamic range in your recording equipment to actually record the data. But then people have been doing preset depth migration, and you discovered that there wasn't so much absorption after all, and the reason it looked so poor is it wasn't being stacked properly. However, I think there's enough evidence in areas with granite that a lot of data does get absorbed, and therefore you're hitting the dynamic range problem, which means you're going to have new acquisition techniques to increase that dynamic range.
Okay, thank you, Chris. Thank you for that.